My name's Steve McGilchrist. I'm WJ Group Business Development Manager. I've been in high friction and PSV, highway PSV since 1982 in various guises, joining what was then ARC, has now become Hanson Aggregates, in the North Wales area, where there's lots of hard stone quarries there producing relatively high PSV materials. So I've done all that through my career. In the last 18 years or so, until joining WJ, I was with a materials manufacturer, manufacturing high friction surfacing systems. So hopefully I know a little bit about what I'm talking about. With WJ, I hasten to add, we are not manufacturers of these systems. I've got no axe to grind with any of these systems. I'm just presenting what's out there. WJ will just use the best systems that we think are out there, out in the marketplace. So, history of high friction started off in London about 1965. Before that, there were attempts, I think, in America to use various systems. And the GLC at the time identified that 70% of all accidents occurred within 15 metres of their junctions, crossings, etc. And so they got together with the Metropolitan Police, Shell and TRL and said, what can we do about this? And developed a high friction surfacing system as an overlay onto existing asphalt. The intention was to increase and enhance the skid resistance of that surface. And they came up with a system with Shell, a two-component bitumen extended epoxy. Epoxy can be used on its own, but it's expensive, so bitumen was used to basically extend and cheapen the product to make it more affordable. And that system became known as Shell Grip. So that system on its own was specified in Series 900 of the Specification of Highway Works, Clause 924. And Clause 924 to this day is the specification which refers to high friction surfacing. So that's just a little bit about the history. Such a success was it that it was promoted quite widely at the time. This was an advert from, I think it was the Journal of the Institute of Highways and Transportation. Also, there were TV adverts. I don't know if you remember this one. I'll just show you this very briefly.
There are thousands of people all over Britain who, while driving on wet roads, have encountered a great danger. When the moment of danger came, they were lucky enough to be traveling on a road surface called Shell Grip. It is estimated that Shell Grip has already saved thousands of people from injury or death. You can be sure of Shell.
Anybody remember that one? Not many of you in this room, looking at the ages of you, I don't think, but it was produced by a guy called Ridley Scott. I wonder what happened to him. So the timeline for the UK, 60s we got bitumen extended epoxy. After that we started getting other systems. In the 80s we got polyurethanes, known as PUs or PURs sometimes, thermoplastic systems, and in 2000 you got methyl methacrylate systems, otherwise known as MMAs, or more commonly known as MMAs. You then had clear epoxy systems and then polyurea systems. So we'll go through those during the course of this presentation. The last few years we've had PU modified MMAs as well. One manufacturer produces those. So what types of high friction system are there? Broadly, there are two generic types, and it's based on the type of binder that's used. The first type is called thermosetting, more commonly known as cold applied systems, and the other type is thermoplastic, otherwise known as hot applied systems. Those terms for each are interchangeable. Thermoplastic, hot applied, it means the same thing. Thermosetting, cold applied, it means the same thing. So what is thermosetting? It's capable of becoming permanently rigid when heated or cured. Typically with a thermoset system, you'll have two components which are mixed together, and once they're mixed, that instigates a chemical curing process which hardens that system. So you'll have two, sometimes it's liquid components that are blended together, sometimes it's a liquid and a powder that's blended together, but the effect of that is to instigate that reaction and to cure the product. When we talk about curing, we mean a hardening process, a polymerization process, where cross-linking occurs and the product becomes rigid. But the thing about that is it's an irreversible change. Once that cure has happened, it's not going to reverse, it's not going to go back. It is what it is. With thermosetting systems, they are supplied as separate components. You have the calcined bauxite aggregate. So when you've mixed the systems together, you get a liquid resin which is starting to cure. You then have to get that onto the road quickly as possible and scatter bauxite on top of it. That bauxite then bonds to that system, and that does then cure to produce your final system. Most thermosets increase in viscosity, either they get more sticky in cold temperatures. It's recommended with some systems you keep them at room temperature before you go out onto site, because otherwise they are too sticky and cold, particularly in winter time, to use. Some systems, such as bitumen extended epoxies, benefit from warming up to about 60 degrees prior to mixing. And the components, whether it be two liquid components or a liquid and a solid, they do require thorough or intimate mixing, as it's known, together. And the rest of it I've already explained about the cross-linking process. And at the end, you apply the binder to the substrate first, and then you scatter the aggregate on top of it, and then that's left to cure to produce your final system. So the types of thermosetting binders are epoxy. You've got pure epoxy, which is typically a clear amber colour, or bitumen extended, which is a black colour because it's been extended with bitumen. Polyurethanes, typically an amber colour. Again, sometimes they can be filled with a powder filler, making a more whitey appearance. Polyureas and methyl methacrylates. MMA's typically a sort of ambery buff colour, sometimes white as well. That's what the types of thermoset binders are. Moving on to thermoplastic, it's capable of softening or fusing when heated and hardening again when cured. It's a reversible process. When you heat a hot applied system, you apply it onto the road hot. When it cools, it hardens, and that becomes your system. However, if that is ever heated up again, it can become soft. So it is a reversible change. You heat typically a thermoplastic system up to about 190 to 210 degrees. But when it's cooled down to normal temperature, it becomes solid. So all thermoplastic systems are relatively similar. They're supplied as a pre-mixed system, normally in plastic bags, and it's pre-batched, pre-dosed at the manufacturers, bagged and supplied on pallets to site, where those bags are normally loaded complete into the preheater. The bag melts down as part of the material, and then it becomes it's heated up to about 190 to 210 degrees, and it becomes liquid to the point where it can be applied onto the road. And it's applied hot as a single process, and when it's cooled, it hardens, as said before. So the types of binder we use in thermoplastics are rosin ester on the left, hydrocarbon, slightly different in appearance. They both do the same job, they've got slightly different characteristics. Thermoplastic and thermoset only refer to the binder aspect of the system, and systems contain various other components, fillers, plasticizers, aggregates, oils, etc. But all high friction systems require calcined bauxite, either in the mix as part of a hot applied system or as a scatter coat as part of a cold applied system. So why calcined bauxite? Well, it's a manufactured aggregate. It's produced in factory conditions from bauxite clay that's quarried out of the ground. It's got properties that are not matched by natural aggregates. It's very blocky in terms of its shape. It's very angular, cubical in a way. It's extremely resistant to abrasion. The aggregate abrasion value is less than 4. High is bad, low is good in AAV terms, and there are bauxites on the market now of less than 1, which is exceptionally hard, and they're approaching diamond in terms of their hardness. That's how hard they are. So they do resist wear very easily, very well. In terms of the skid resistance, the PSV is, the specification says 70 plus, but 80 to 85 is not uncommon and is the norm really in these sorts of products. Highly resistant to polishing. It really doesn't polish, and because of that hardness, there is no appreciable polishing that occurs with calcined bauxite. And it is the defining constituent of high friction surfacing. If it's not got calcined bauxite in it, it's not a high friction surfacing. So look at the different types of bauxite. On the left, you've got Guyanan, very grey in colour. That was really the first material that came on the market when GLC were doing the trials in 1960s. Guyanan was about the only bauxite around at that time. But since then, bauxite's come in from China. They've also come in from India as well. And China, you'll see, has got not only a buff material, but it's got a grey as well. And the reason they've got different coloured materials is because they're calcined at different temperatures. The buff is typically calcined about 1600 degrees, the grey about 800, and it gives them different colouring, different characteristics. And more recently, we've got the Indian bauxites on the market. They're more of a grey-brown colour. Again, very good material, and they are used widely on the network out there because they all meet the spec required for high friction. So the buff bauxite in China will be produced typically in a shaft kiln. That's the method of manufacture. It's fed in at the top and it's heated to about 1600 degrees for some time, some considerable time, and then it's fully calcined. It's basically, if you think of pottery, it's the same process using firing pottery, and it produces that manufactured aggregate. The other technique is a rotary kiln. This is more similar to a cement works. If you've ever been to a cement works, the way cement is manufactured, it's fed in at one end and it's heated and it goes round and round and it's constantly being pushed along that shaft, the rotary kiln to the output. By the time it gets to the end, it's been fully calcined. Typically, though, that's at a low temperature. Okay, so RSTA have its own specification for calcined bauxite for high friction. I've highlighted the important sections in pink there. So you've got your PSV has to be 70 plus, AAV has to be less than 4. I'm sorry if it's very small for you there. And the other key thing is the aluminium oxide content has to be greater or equal to 82%. And it is that aluminium oxide content known as corundum that is very important in giving calcined bauxite its characteristics. So these are different cold applied systems, different appearance. On the left is a typical bitumen extended epoxy, how that looks when it's spread. And on the right, could be a PU, could be a pure epoxy resin system, but it's got that typical amber appearance. Okay. So for cold applied systems, the tools and equipment needed are relatively small. You need a high torque drill to mix your components together, the mixing paddle that goes with that. Once that's done, these are the key components: a flat bladed squeegee and a serrated squeegee. Well, you'd use a flat-bladed squeegee if you were pre-treating the road surface. If the road was highly negatively textured, i.e. you would get a lot of binder drainage into the surface, you would use typically a pre-treatment, and some of the systems on offer here from the manufacturers here do offer pre-treatments, scratch coats as they're known, which you would put on the surface and then you'd scrape over the surface with your flat-bladed squeegee prior to going over the top with your cold applied system. Once you've done that, and even if you don't need to do that, there are occasions when you don't need to do that, you then go on top of that surface with your cold applied system. So you'd mix your components together, you'd then spread it onto the surface, but then you would regulate that film of resin with a serrated squeegee. It gives you a fixed amount of thickness of resin on that surface. So in terms of how you'd apply cold applied, good practice is to group your components together. If you're using 2 or 3 components in your particular mix, the good practice is to group them together beforehand so you don't forget to put one in, so you can easily see if you're missing one. If you need, which you do, bauxite, place the sacks of aggregate where they're needed on site. Don't have them all in one place, then find you've got to run 50 metres with aggregates to scatter it onto the surface. Have them where you need it. So place it around the job where needed. It makes it a lot easier, believe me. You mix the base material together, and then you add the catalyst, the hardener and or catalyst whilst being mixed. You then continue mixing for typically 2 to 3 minutes, and then pour onto the road surface. Once you've done that, spread using a serrated squeegee. taking care always to maintain a wet edge. So when the next mixed batch comes along, there's still a wet edge to tie into. If you lose that wet edge, you're then going to get a physical boundary border between your next one, which is a weak spot. So once you start mixing and using cold applied systems, it's a race in time. You've got to basically go from start to finish. You can't stop and have a sandwich halfway through. You've got to keep it going. So you've got your wet film of resin on the surface. You then you scatter your aggregate on top. And typically it is a scattering technique. You don't dump the bag on and start pushing it around with a broom. That's not ideal. The best technique is to scatter it onto the surface as you would do bird seed or sown, so any type of seed. And you do it to excess. So you put on more calcined bauxite onto that surface than you actually need. Typically, you put it on to start with and you start seeing wet patches appearing, which is where it's sunk into the resin. So you have to keep alert to that and keep going over it until those wet patches no longer appear. But once that's done, you remove your masking tape while the resin's still wet, because once it's cured, it's a real bugger to get the resin off, to get the tape off. And then once the system has cured, you can sweep off the excess chippings and it leaves you with your high friction surfacing. So that's the system with all the components together. Good practice, so you're not going to miss one mixing in. It is easy to do. You know, things are going on around you on site. There's traffic, typically. It's easy to miss one, so it's good practice to put them all together. And we've got a quick video on how it's done. Actually, two different processes there. The first part you saw, the guy's using a flat-bladed squeegee. He's doing a scratch coat, and he very quickly switches to the final system where the resin is sitting on top of the surface. So just be aware of that. But that it's very short, but that's your cold applied system. So. Moving on to thermoplastic or hot applied, the differences are you have the material supplied in low melt sacks. It's a granular material. It's supplied as a almost like it's not a powder. It's a granulated material, typically 1 to 3 mil material in there with the prills of resin. It's homogeneous because it's been mixed in a factory, so every sack should be the same as the next sack. You do need special equipment. You need boilers with powerful mixing paddles to mix it, because it's quite a difficult and hard material to mix. You've got all that aggregate in there you're trying to turn over. Mixing temperatures up to 192, 20 degrees. So it does take a while to get your batch of material up to the right temperature before it's used. And those preheaters are typically using gas burners underneath. Sometimes they're oil jacketed, sometimes they're direct heat, but they are using a flame. It's the only way we know at the moment to get enough heat into that material quickly enough on site to make it viable. You do get some odour when you get up to that temperature. You get a bit of smell with thermoplastic systems. You get smell with some of the cold applied systems as well. So just be aware of that. It's suitable for asphalt substrates, not generally for concrete. Whereas some of the cold applied systems can be used for both. And the temperature range for thermoplastic is 0 to 35. It does vary with some of the cold applied systems, the temperature which you can apply them at, which we'll come on to in a minute. Okay, so in terms of application for thermoplastic, in the same way as for cold applied, you mask off your drain covers, your white lines, everything that you don't want the system to be applied to, you mask off. You check the temperatures within the specified range, that's 0 to 35 degrees. You, having mixed the material, you draw it off into a bucket or jug, and then you apply it in strips transversely, usually across the road. I've seen it done longitudinally as well, but normally it's transversely across the road using a screed mould. screen mould about 300 millimetres wide. It's poured into there, then pulled across to produce an even layer of material. And at the end of that pull, you've got material left in your mould. You've got to push it back over the surface again to lose it, because obviously you'd end up with a lump of material if you just left it there. Then you move to the next pull. And the aim is to overlap the previous one by about 25 millimetres, so you get a tie-in with it and you don't leave gaps there. Again, pull up the tape as work progresses whilst material is still hot and pliable, because if you leave it till it's cured, you won't get all that tape off and it'll look a mess. And allow it to cool. And then once it's cooled, it's suitable for use. Okay? So this is the guy loading the sacks. That's how it's supplied. This is High-Tech's system as it happens. That's how it's supplied. He's loading it into his boiler. And it just goes in complete like that, so that he doesn't have to split the bag down and pour the material out. It just puts the whole bag in there, it melts down. He's there waiting for it to be ready to pour out. And it will come out, he'll pour it out into his bucket and then pour into the screed mould. Usually somebody else is doing that. But you need two men, you need one to pour, one to pull. You see the visible differences between the hot system and the cold. With the hot system, you do get visible lines. I mean, good operatives can, get to the point where you don't see them very easily. But with cold applied systems, you get one continuous layer of material with no joints, no visible joints in there at all. With hot applied, you do tend to see the joints. So that's a visual difference that you see. So looking at the comparisons of the different systems, this is going back into the past. With performance, you were tending to look at cold applied systems, epoxies, polyurethanes, and if you wanted quick cure speed, you're looking at hot applied systems. And there'll be a table I'll come on to in a minute to look at the different cure speeds involved. But more recently, you've been able to get both, because with MMAs, you not only get a quick cure speed, you do get the performance and durability. But it does come at a price normally, so you pay as your money takes your choice. They do tend to work out more expensive. But in today's situation with road closures, you don't want any sort of downtime. You're looking to try and get the road back into use as quickly as possible, and it's often worth the extra cost of MMA polyurea if you're in those particular situations. So this is a table showing the different, primarily the different cure times that you have there. You've also got the installation temperatures there. With the epoxy, you're looking at a minimum temperature of about 5 degrees up to about 35. PU, 5 degrees. Some systems go down to 0. You can use them at 0. But with some of the ones on the right-hand side, the polyureas, rosin esters and MMAs, you can lay them as low as 0 degrees, up to about 40. Now, whatever temperature you lay it at, it does affect the cure speed. So with epoxy at 25 degrees, you're looking at 2 to 3 hours cure time, which is fine. At 5 degrees, you're up to 10 hours. And really, for most people, most highway engineers, that's too long to have to wait for something to cure. Polyurethanes, again, it does vary with time, going up to about 4 hours at 5 degrees. That's about right, because I've seen that. Going over to hot applied systems, again, they work by cooling. So when the road itself is hot, it takes about 50 to 60 minutes for it to cool down, but when the road itself is cold, it takes far less, about 30 minutes. And MMA's 25 degrees, about 30 minutes cure time, and 5 degrees, about 60. So different systems have different properties, and you pay your money and takes your choice. All of those systems are BBA Type 1 approved. Different manufacturers have their own certificates for those systems. They all comply with the BBA requirements. So, very briefly, BBA scheme, it requires a product to be approved by them, working to their guidelines document. There's a series of tests and criteria that the system has to meet to be approved. But it doesn't just end there, because with high friction, and this doesn't apply to other HAPAS categories, but with high friction, the installer has to be approved as well by the BBA. So it's a system of product and installer, and watch out for that. If you want to know about which systems and installers are approved at any time, go onto the BBA website, bbacerts.co.uk, as I think from memory. Okay, so you go through the BBA assessment for your system, and that determines categorisation as type 1, 2 or 3, and that categorisation depends on the traffic count in any particular given site, whether the system is suitable for a high traffic count or a lower traffic count. In practice, over time, there's only one criteria in the game, and that's type 1. Nobody talks about type 2s or type 3s anymore. Type 1 is the only system, and that can be used in the highest traffic count that's out there. So it's become a bit of I mention it, but it's not really relevant too much anymore. What the BBA does as far as in system holders or manufacturers conduct regular factory audits and assessments of the system's performance in use. Those are the traffic categories, but really, as I say, type 1 has higher criteria for the system manufacturer, and it is the only system that people really ask for these days. And again, it's based on traffic count. Type 1 has the highest traffic count there. That's up to 3,500 commercial vehicles per lane per day. This is a good document worth looking at. It's on the RSTA website. Please have a look at it, but it's well worth a read. I've just done a couple of extracts from it here, which is that sheet and this one here. So it tells you for various types of surface treatment how long you should expect them to last. And these are figures, they're not just plucked out of the air, these are based on empirical evidence that has been obtained in the field. So you're looking at high friction surface in a hot applied system, typically its life is about 8 years, and a cold applied system about 12 years. There will be examples of shorter and longer life, but from the evidence we've got and the BBA has found, those are the lives you should expect. So the key considerations when you're looking at high friction and what type to choose are the traffic count in commercial vehicles per day, type 1, 2 or 3, but again really type 1 is the only one that's around. The time of year, because cold applied is best applied generally in, well, can be applied throughout the year, but if cure time is an issue, then the summer months, the warmer months are best for cold applied. Hot applied can be used throughout the year and is used in Scotland particularly throughout the year. But that is a factor in your decision. Site access, traffic management. I say that because hot applied systems generally require bigger trucks with boilers on, etc., whereas you can get away with smaller trucks and less equipment for cold applied. The time allowed working window and the consequences of a breach of that working window are factors as well. If cure time is critical, then that will affect your decision on what system to choose. Type of substrate, asphalt or concrete. As we've said before, hot applied systems generally aren't applied on concrete. Certain cold applied systems can be applied to both. The BBA certificate just looks at asphalt, but there is an extra test you can have which certifies the product for use on concrete as well, and look out for that. Substrate texture, will a scratch coat be needed? It's an extra process, it's extra time. If that's needed, then factor that into consideration. The aesthetics, does it matter if there's visible joints on the surface? If so, then that will determine your choice as well. Your service life requirement is a factor as well. If your asphalt surface is not going to last 12 years, you might wonder whether it's worth having a cold applied system. You might decide to have a hot applied system instead. And the cost, obviously. But the advice I'd give anybody is work with your specialist contractor to achieve the best solution. Talk to the people you're dealing with. They're generally experts in what they do and they'll give you good advice. Thank you very much.